So the match pairs test on page 67 is the hypothesis test that requires probably the most background work in the calculator. It's nothing too crazy, but it's just more than what we've had to do. The function you'll see here is still a t-test, like a one population mean hypothesis test. So there's really nothing in terms of like the interpretation that's going to be any different there. It's just a question. I mean, it's a slight difference, but the big difference comes in what we put into the calculator and how we use that information. All right, we have a raw list of data, and that's typically what's going to happen when you're dealing with a match pair situation. So the before values go in L1. The after values go in L2. So let's take a second and jot those values in. I regret not doing that beforehand, so part of this video is just going to be you watching me type stuff into the calculator, unfortunately. However, you can... Do they call it fast forward anymore? But you could advance the video, so you don't have to actually watch me do it. You can speed it up. Dead air makes for good television. It's like when you're watching a baseball game and they say, you know, let the game breathe. The problem is when you get out of class at night and you throw on a Mets game or a Yankee game and they're letting the game breathe, aka they're not speaking at all you hear is static, and you're like, is my radio broken? And then they start talking, and there's the 0-1 pitch. Line to center field. Letting the game breathe, I think, removes any excitement from the broadcast. For you sports fans out there, I'll give you an Easter egg. I can only deal with Mets and Yankees. I mean, I'm not a Yankee fan, but I do listen to their broadcasts from time to time. So I will, as an Easter egg, take and this is going to require a little bit more work, a YouTube video or any other sort of audio clip sent to me that is a home run call by any of the Yankee announcers or any of the Mets announcers. All right, so that would be the Easter egg. I mean, I guess it's for anyone, but obviously the sports fans have a little bit of a leg up. All right, so I'll give some for other kind of fans out there, but we'll see. Anyway, we put the information in the calculator without even reading the problem. And of course, it's a sports-related problem, so there's a little bit of a theme there. Of course, it's football, though. Use a 0.05 significance level. Test the claim that there's no significant difference between the average New York Giants winning percentage before and after a bye week between 1996 and 2004 seasons. A little background for those who might be interested. Somebody back, I would imagine around 2004. I don't actually remember the year that I took note of this information. It had to be around that time. But an announcer said something like, the Philadelphia Eagles always win after a bye week. And the Giants always win before the bye week, but always lose after the bye week. Not always, but they were saying like their record is terrible after the bye week compared to Andy Reid, who was the coach of the Philadelphia Eagles at the time. So I was like, you know what? I wonder if there's something to that. So I was looking at it like just winning percentage in general, not the specific game prior, but I just took all the games prior to the bye week and all the games after the bye week just to see if there was any kind of relationship. Maybe, like it's a kind of a line of demarcation between success and failure. So I was curious. So that was the idea behind this. If it inspires you to do something similar, that's a good thing. All right, so what we're looking for here is to see if there's a significant difference between, and that's all it is, significant difference, better or worse, doesn't matter, all right, between the winning percentages, the average winning percentage, so that's a mean, before and after a bye week. So the null is always going to involve an equal sign, so mu1 is equal to mu2. The alternative, a difference, would be that there's a difference. A difference would be that the first population proportion is not going to be the same as the second one. The alpha value is 0.05. That was given to us. The calculator test is a t-test. And, you know, the kind of sneaky part of the process here is the p-value, where it's like, all right, now just go ahead and figure out the p-value. Well, that's the hard part. You know, that's the part where you got to do the work. All right, so in your calculator, what you're going to do is you're going to bring your cursor right up onto the L3 and hit enter. We've done this before. When you hit enter, it'll bring the blinking cursor down onto L3 in the bottom row. We've done this before when we were working with binomial distribution, so this should not be foreign to you. But we're not going to do anything crazy here. All we're going to do is type in L1 minus L2. And then hit enter. If you get an error message, it's because you tried doing it in the first cell. All right, so I'll show you real quick. So if I do it here, you see where it says L3 of 1, L1 minus L2, that's going to be a problem. No good. But if I do it right up top, hit enter, and then L1 minus L2, it'll subtract every L2 value from the corresponding L1 value. So then what you do is quit out of here, so second mode, stat, test, all you're looking at is the t-test. All right, here we're working with data. In the previous time that we used the calculator for a t-test, we were working with stats because we were given raw stats. But now we're working with data because we typed in data, right? I said raw stats. What I meant was summary stats. Now we have raw data, all right? So the mu sub O is a weird kind of thing because that's the value that corresponds to your null hypothesis, all right? And so I'm just going to kind of bring it in and take a look at that real quick. What this means is that mu1 minus mu2 is equal to 0. All right? And that is the same as saying that the difference between the means, mu sub d, is equal to 0. All right? So this is the value that goes into the calculator. All right, this goes in for mu sub O. All right. And that's where that number comes from. So if a question says something like, test the claim that the mean for the first group is 0.2 more than the mean for the second group, that would be different. The difference would be 0.2. So that would be the number that goes in. But here, it's just an equality, all right? So the list would be L3, second 3. The frequency is 1 because each one of those values occurs once. I'm using a not equal symbol in my alternative hypothesis, so that's that. Oops, hit the wrong thing. And then right to calculate. And so what we get is the p-value of 0.453. All right, that's a fairly large p-value. And honestly, and I'll make a note here, p-value greater than alpha. So that means that we're not going to reject the null hypothesis. And what I was going to say is, honestly, that means that it kind of begs the question of why was this test being conducted to begin with? Because it was very clearly not the case that there was a significant difference between the percentages. You know, like, and it's kind of weird because you look at it and say, well, what about that point 0.8, the 0.182? And then the answer, somebody else might reply, well, what about the 0.718 and 0.778? You know, like most of the years, those percentage values are pretty close to one another. There's only a couple where it's like, whoa, it's a little out of whack. And the bottom line is, you know, this is a team over a course of like a decade. Yeah, so they sucked for 2 years, like really sucked. You know, that happens. You know, for each year where they started off strong, like '03 and '04, but then ended up being terrible after that, there's a year or two where they started off poorly, like '01, and finished strong. So it balances itself out at the end. All right. But generally, in that span of time, the Giants were pretty bad, except for 2000, where they went to the Super Bowl and then got decimated. Just curious if that actually works mathematically. 35-7, I believe, was the final score. No, it's not. They scored 20% compared to, no, they scored 1/5. Yeah, 1/5 of their opponent's scores. So, yeah, only 20%. So they got double decimated. All right, so there's sufficient evidence to reject the claim that the population mean winning percentages I'm going to say win percents are the same, or equal is fine, as long as you write the word equal at the 0.05 significance level. Therefore, the claim that there is a significant difference is going to be, so insufficient. All right, so let's zoom out, take a look. Insufficient evidence to reject, again, the first sentence always addresses the null. If there's not enough evidence to reject the null, we're keeping the null, which means the alternative is not true, making it false.